genuine well-wishers, constructive critics. I take it for granted that you and your beloved are in a fine fettle. It is social activist come good-hearted preacher, Suresh back with altruistic ecstasy for my 100th video on annual of publication on YouTube today, 23rd October 2020, Friday. Let me reintroduce myself for the benefit of those that started watching my videos only recently. I am Professor S. Suresh, working with the Faculty of Mechanical Engineering at Dr. MGR Educational and Research Institute, a leading deemed to be university in India, located in the heart of Chennai, capital of Tamil Nadu, South India, in operation for more than 3 decades. I started my channel on YouTube precisely on 11th April 2020. My first video was on engineering graphics, which was a prerequisite for the online course I was conducting that time during the lockdown. I pursued that group practice, which has become a hobby and passion now, and publish videos on varied topics encompassing engineering, medical, social activism, management, nature, etc. Today, I am in the process of publishing my 100th video, and this time my presentation will cover mechanical engineering from Stone Age era, the basic necessity for Earthlings. For your information, I am basically a mechanical engineer. Now you know why I have selected this particular topic for my 100th video. I dedicate all my videos to the Supreme God. My mentor, Dr. G. Gopalakrishnan, Provost of a university, is also a mechanical engineer by profession, for your information, and my family members besides my parents. Mechanical engineering is one of the core disciplines of engineering, other ones being civil engineering, electronics, and electrical engineering. Out of this, mechanical engineering happens to be the first engineering discipline, since during the Stone Age era, everybody used to consume meat besides vegetables, fruits, nuts, etc. And for hunting, they made weapons from stones in a conventional way, manually. That's how engineering commenced, even though they did not call it as engineering that time. Engineering is the use of scientific principles to design and build machines, structures, and other items, including bridges, tunnels, roads, vehicles, and buildings. The discipline of engineering encompasses a broad range of more specialized fields of engineering, each with a more specific emphasis on particular areas of applied mathematics, applied science, and types of application. The term engineering is derived from the Latin term ingenium, meaning cleverness, and engineer, meaning to contrive, device. The essence of engineering is innovation, thinking differently, applying lateral, also known as divergent thinking skills. Engineering originated basically from physical sciences, especially physics, besides chemistry, and to a certain extent biology. The American Engineers Council for Professional Development, the predecessor of ABET, has defined engineering as the creative application of scientific principles to design or develop structures, machines, apparatus, or manufacturing process or works, utilizing them singly or in combination, or to construct or operate the same with full cognizance of the design, or to forecast their behavior under specific operating conditions. All as respects an intended function, economics of operation, and safety to life and property. Engineering has existed since ancient times, when humans devised inventions such as wedge, lever, wheel, pulley, etc. It's all mechanical engineering, as you can see. The term engineering is derived from the word engineer, which itself dates back to the 14th century, when an engineer, literally one who builds or operates a siege engine, referred to a constructor of military engines. In this context, now obsolete, an engineer referred to a military machine that is a mechanical contraption used in war. That is, for example, compatible. Notable examples of the obsolete usage which have survived to the present day are military engineering corps. Example, the US Army of Corps of Engineers. Corps of Engineers. The word engine itself is of even older origin, ultimately deriving from the Latin ingenium, meaning innate quality, especially mental power, hence a clever invention. Later, as the design of civilian structures such as bridges and buildings matured as a technical discipline, the term civil engineering entered the lexicon as a way to distinguish between those specializing in the construction of such non-military projects and those involved in the discipline of military engineering. The pyramids in ancient Egypt, ziggurats of Mesopotamia, the Acropolis and Parthenon in Greece, the Roman aqueducts via Appia and Colosseum, Teo, Teotihuacan, and the Brigadeshwara Temple of Tanjore, among many others, stand as a testament to the ingenuity and skill of ancient civil and military engineers. Other monuments no longer standing, such as the Hanging Gardens of Babylon, there is no historical proof of it, and the Pharos of Alexandria were important engineering achievements of the time and were considered among the seven wonders of the ancient world. The six classic simple machines were known in the ancient Near East. The wedge and the inclined plane ramp were known since prehistoric times. The wheel, along with the wheel, is a wonderful invention. The wheel, along with the wheel and the axle mechanism, was invented in Mesopotamia, modern Iraq, during the 5th millennium BC. The lever mechanism first appeared around 5,000 years ago in the Near East, where it was used in a simple balance scale and to move large objects in ancient Egyptian technology. The lever was also used in the shed of water lifting device, the first crane machine, which appeared in Mesopotamia circa 3000 BC and then in ancient Egyptian technology circa 2000 BC. The earliest evidence of pulleys dates back to Mesopotamia in the early 2nd million BC and ancient Egypt during the 12th dynasty, 1991 to 1802 BC. The screw, the last of the simple machines to be invented, first appeared in Mesopotamia during the Neo-Assyrian period, 911 to 609 BC. The Egyptian pyramids were built using three of the six simple machines, the inclined plane, the wedge, and the lever, to create structures like the Great Pyramid of Giza. The earliest civil engineer known by name is Imhotep. As one of the officials of the pharaoh Djoser, he probably designed and supervised the construction of the Pyramid of Djoser, the Step Pyramid, at Saqqara in Egypt around 2060 to 2006-11 BC. The earliest practical water-powered machines, the water wheel and water mill, first appeared in the Persian Empire in what are now Iraq and Iran by the early 4th century BC. Kush developed the Sakya during the 4th century BC, which relied on animal power instead of human energy. Hafirs were developed as a type of reservoir in Kush to store and contain water as well as boost irrigation. Sappers were employed to build causeways during military campaigns. Kushite ancestors built spears during the Bronze Age between 3700 and 3250 BC. Bloomeries and blast furnaces were also created during the 7th centuries BC in Kush. Ancient Greece developed machines in both civilian and military domains. The Antikythera mechanism, an early known mechanical analog computer, and the mechanical inventions of Archimedes are examples of Greek mechanical engineering. Some of Archimedes' inventions, as well as the Antikythera mechanism, require sophisticated knowledge of differential gearing or epicyclic gearing, two key principles in machine theory that helped design the gear trains of the Industrial Revolution and are still widely used today in diverse fields such as robotics and automotive engineering. Ancient Chinese, Greek, Roman, and Hunnic armies employed military machines and inventions such as artillery, which was developed by the Greeks around the 4th century BC. The trireme, the ballista, and the catapult. In the Middle Ages, the trebuchet was developed. The science of classical mechanics, sometimes called Newtonian mechanics, formed the scientific basis of much of modern engineering. Canal building was an important engineering work during the early phases of Industrial Revolution. The Industrial Revolution created a demand for machinery with metal parts, which led to the development of several machine tools. Mechanical engineering is the design and manufacture of physical or mechanical systems such as power and energy systems, aerospace, aircraft products, weapon systems, transportation products, engines, compressors, powertrains, kinematic chains, vacuum technology, vibration isolation equipment, manufacturing robotics, turbines, audio equipment, and mechatronics. Mechanical engineering is an engineering branch that combines engineering physics and mathematics principles with the material science to design, analyze, manufacture, and design mechanical systems. It is one of the oldest and broadest of the engineering branches. The mechanical engineering field requires an understanding of core areas including mechanics, dynamics, thermodynamics, material science, structural analysis, and electricity. In addition to these core principles, mechanical engineers use tools such as computer-aided design, shortly CAD, computer-aided manufacturing, shortly CAM, and product lifecycle management to design and analyze manufacturing plants, industrial equipment and machinery, heating and cooling systems, transportation systems, aircraft, watercraft, robotics, medical devices, weapons, and others. It is a branch of engineering that involves the design, production, and operation of machinery. Mechanical engineering emerged as a field during the Industrial Revolution in Europe in the 18th century. Do you know the present industrial revolution? We have moved over to fourth industrial revolution, which is called Industry 4.0, Industrial Internet of Things, IIoT. However, its development can be traced back several thousand years around the world. In the 19th century, developments in physics led to the development of mechanical engineering science. The field was continually evolved to incorporate advancements. Today, mechanical engineers are pursuing developments in such areas as composites, mechatronics, and nanotechnology. It also overlaps with aerospace engineering, metallurgical engineering, civil engineering, electrical engineering, manufacturing engineering, chemical engineering, industrial engineering, and other engineering disciplines to varying amounts. Mechanical engineers may also work in the field of biomedical engineering, specifically with the biomechanics, transport phenomena, biomechatronics, nanotechnology, and modeling of biological systems. The earliest practical water power machines, the water wheel and the water mill, first appeared in the Persian Empire in what are now Iraq and Iran by the early 4th century BC. In ancient Greece, the works of Archimedes, 287 to 212 BC, included mechanics in the Western tradition. In Roman Egypt, Heron of Alexandria, c. 10 to 70 AD, created the first steam-powered device, Eolify. In China, Zhang Heng, 78 to 139 AD, improved a water clock and invented a seismometer, and Ma Jun, 200 to 265 AD, invented a chariot and with the differential gears. The medieval Chinese horologist and engineer Su Sang, 1020 to 1101 AD, incorporated an escapement mechanism into his astronomical clock tower 2 centuries before escapement devices were found in medieval European clocks. He also invented the world's first known endless power transmitting chain drives. During the Islamic Golden Age, 7th to 15th century, Muslim inventors made remarkable contributions in the field of mechanical technology. Al-Jazari was one of them, wrote his famous book of ingenious devices in 1206 and presented many mechanical designs. Al-Jazari is also the first known person to create devices such as the crankshaft and camshaft, which now form the basis of many mechanisms. During the 17th century, important breakthroughs in the foundations of mechanical engineering occurred in England. Sir Isaac Newton formulated Newton's laws of motion and developed calculus, the mathematical basis of physics. Newton was reluctant to publish his works for years, but he was finally persuaded to do so by his colleagues, such as Sir Edmund Halley, much to the benefit of all mankind. Gottfried Wilhelm Leibniz is also credited with creating calculus during this time period. During the early 19th century Industrial Revolution, machine tools were developed in England, Germany, and Scotland. This allowed mechanical engineering to develop as a separate field within engineering. They brought with them manufacturing machines and the engine to power them. The first British Professional Society of Mechanical Engineers was formed in 1847, Institution of Engineers 30 years after the Civil Engineers formed the first such professional society, Institution of Civil Engineers. On the European continent, Johann von Zimmermann, 1820 to 1901, founded the first factory for grinding machines in Chemnitz, Germany in 1848. In the US, the American Society of Mechanical Engineers, ASME, was formed in 1880, becoming the third such professional engineering society after the American Society of Civil Engineers in 1852, the American Institute of Mining Engineers in 1871. The first schools in the US to offer an engineering education were the US Military Academy in 1817, an institution now known as Norwich University in 1819, and Rensselaer Polytechnic University Institute in 1825. Education in mechanical engineering has historically been based on a strong foundation in mathematics and science. The fundamental subjects of mechanical engineering usually include mathematics, in particular calculus, differential equations, and linear algebra, basic physical sciences including physics and chemistry, statics and dynamics, strength of materials and solid mechanics, materials engineering, composites, thermodynamics, heat transfer, energy conversion, and HVAC. heating, ventilation, and air conditioning systems. Fuels, combustion, internal combustion engines, ICE engines. Fluid mechanics, including fluid statics and fluid dynamics. Mechanism and machine design, including kinematics and dynamics. Kinematics is one part of dynamics. I don't know why they are separating kinetics and kinematics. Instrumentation and measurement, manufacturing engineering, technology or process, vibration control theory and control engineering, hydraulics and pneumatics, mechatronics and robotics, engineering design and product design, crafting, computer-aided design, CAD, and computer-aided manufacturing. Computer-aided design, shortly CAD, computer-aided manufacturing, shortly CAM. There are always short forms to confuse the people. Mechanical engineers are also expected to understand and be able to apply basic concepts from chemistry, physics, tribology, chemical engineering, civil engineering, and electrical engineering. All mechanical engineering programs include multiple semesters of mathematical classes, including calculus and advanced mathematical concepts, including differential equations, partial differential equations, linear algebra, abstract algebra, and differential geometry, among others. Mechanical engineers research, design, develop, build, and test mechanical and thermal devices, including tools, engines, and machines. Mechanical engineers typically do the following: analyze problems to see how mechanical and thermal devices might help solve the problem, design or redesign mechanical and thermal devices using analysis and CAD, develop and test prototypes of devices they design, analyze the test results and change the design as needed, oversee the manufacturing process for the device. Mechanical engineers design and oversee the manufacturing of many products ranging from medical devices to new batteries. They also design power producing machines such as electrical generators, internal combustion engines, and steam and gas turbines, as well as power using machines such as refrigeration and air conditioning systems. Like other engineers, mechanical engineers use computers to help create and analyze designs, run simulations, and test how a machine is likely to work. I want to tell you something. Computer is a machine, just like any other machine. Nothing big or smaller than that. The field of mechanical engineering can be thought of as a collection of many mechanical engineering science disciplines. Some of these disciplines are unique to mechanical engineering, while others are a combination of mechanical engineering and one or more other disciplines. Most work that a mechanical engineer does uses skills and techniques from several of these sub-disciplines as well as specialized sub-disciplines. Mechanics is, in the most general sense, a study of forces and the effect upon matter. Matter is bodies and particles, okay, in space. Typically, engineering mechanics is used to analyze and predict the acceleration and deformation, both elastic and plastic, of objects and unknown forces, also called loads or stresses. Sub-disciplines of mechanics include statics, the study of non-moving bodies under known loads, how forces affect static bodies. Dynamics is a study of how forces affect moving bodies. Dynamics include kinematics, about movement, velocity, and acceleration, and kinetics, about forces and resulting accelerations. Mechanics of materials, the study of how different materials deform under various types of stress. Fluid mechanics, the study of how fluids react to forces. Kinematics, the study of motion of bodies, objects, and systems, group of objects, while ignoring the forces that cause the motion. Kinematics is often used in the design and analysis of mechanisms. Continuum mechanics, a method of applying mechanics that assumes that objects are continuous rather than discrete. Mechanical engineers typically use mechanics in the design of analysis phases of engineering. If the engineering project were the design of a vehicle, statics might be employed to design the frame of the vehicle in order to evaluate where the stresses will be most intense. Dynamics might be used when designing the car's engine to evaluate the forces in the pistons and cams as the engine cycles. Mechanics of materials might be used to choose appropriate materials for the frame of the engine. Fluid mechanics might be used to design a ventilation system for the vehicle or to design the intake system for the engine. Mechatronics is a combination of mechanics and electronics. From the term itself, you can make out it's an interdisciplinary branch of mechanical engineering, chemical engineering, not chemical, electrical engineering and software engineering that is concerned with integrating electrical and mechanical engineering to create hybrid systems. Hybrid means combination. In this way, machines can be automated through the use of electric motors, servo mechanisms, and other electrical systems in conjunction with the special software. A common example of a mechatronic system is a CD rounder. Mechanical systems open and close the drive, spin the CD, and move the laser, while an optical system reads the data on the CD and converts it into bits. Integrated software controls the process and communicates the contents of the CD to the computer. Robotics is application of mechatronics to create robots. They are often used in industry to perform tasks that are dangerous, unpleasant, or repetitive. These robots may be of any shape and size, but all are pre-programmed and interact physically with the world. To create a robot, an engineer typically employs kinematics to determine the robot's range of motion, and mechanics to determine the stresses within the robot. Robots are used extensively in industrial engineering. They allow businesses to save money on labor, perform tasks that are either too dangerous or too precise for humans to perform them economically, and to ensure better quality. They are used even in surgeries and all that to assist the surgeons. So many movements that we cannot do, we can attain with the help of robots. Many companies employ assembly lines of robots, especially in automotive industries, and some factories are so robotized that they can run by themselves. Outside the factory, robots have been employed in bomb disposal, especially the mine disposal, in space exploration, and many other fields. Robots are also sold for various residential applications, from recreation to domestic applications. There are robot maids, robo pets. Structural analysis is a branch of mechanical engineering and also civil engineering devoted to examining why and how objects fail and to fix the objects of their performance. Structural failures occurs in two general modes: static failure and fatigue failure. Static structural failure occurs when, upon being loaded, having a force applied, the object being analyzed either breaks or is deformed plastically depending on the criterion for failure. Fatigue failure occurs when an object fails after a number of repeated loading and unloading cycles. Fatigue failure occurs because of imperfections in the object. A microscopic crack on the surface of the object, for instance, will grow slightly with each cycle propagation until the crack is large enough to cause ultimate failure. Failure is not simply defined as when a part breaks, however, it is defined as when a part does not operate as intended. Some systems, such as the perforated top sections of some plastic bags, are designed to break. If these systems do not break, failure analysis might be employed to determine the cause. Structural analysis is often used by mechanical engineers after failure has occurred or when designing to prevent failure. Even aircraft, whenever there is an accident or some bomb, this thing, the flight goes off in mid-air, structural analysis is applied. Once theory is applied to mechanical design, physical testing is often performed to verify calculated results. All of you know about this thing, Titanic. There also they did structural analysis. Okay, structural analysis may be used in an office when designing parts, the field to analyze failed parts, or in laboratories where parts might undergo controlled failure tests. Thermodynamics is an applied science used in several branches of engineering, including mechanical and chemical engineering. At its simplest, thermodynamics is a study of energy, its use and transformation through a system. Typically, engineering thermodynamics is concerned with changing energy from one form to another. All of you know the law of conservation of energy. Energy can neither be destroyed nor created, it can only be transformed from one form to another. As an example, automotive engines convert chemical energy, enthalpy, from the fuel into heat, and then the mechanical energy, then into mechanical energy that eventually turns the wheels. Thermodynamic principles are used by mechanical engineers in the fields of heat transfer, thermofluids, and energy conversion. Mechanical engineers use thermoscience to design engines and power plants, heating, ventilation, and air conditioning, HVAC systems, heat exchanger, heat sinks, radiators, refrigeration, insulation, and others. Drafting or technical drawing is a means by which mechanical engineers design products and create instructions for manufacturing parts. A technical drawing can be a computer model or hand-drawn schematic showing all the dimensions necessary to manufacture a part, as well as assembly notes, a list of required materials, other pertinent information. A used mechanical engineer or skilled worker who creates technical drawings may be referred to as a drafter or draftsman. Those designations are gone now. Nowadays, people use computer packages. Drafting has historically been a two-dimensional process, but CAD programs now allow the designer to create in three dimensions. Instructions for manufacturing a part must be fed to the necessary machinery, either manually through programmed instructions or through the use of a CAM or combined CAD-CAM program. Optionally, an engineer may also manually manufacture a part using the technical drawings. However, with the advent of computer numerically controlled CNC manufacturing, parts can now be fabricated without the need for constant technician input. All of you know about the 3D printing and all that, right? Additive manufacturing. Manually manufactured parts generally consist of spray coatings, surface finishes, and other processes that cannot economically or practically be done by a machine. Drafting is used in nearly every sub-discipline of mechanical engineering by many other branches of engineering and architecture. Three-dimensional models created using CAD software are also commonly used in finite element analysis (FEA) and computational fluid dynamics (CFD). Many mechanical engineering companies, especially those in industrialized nations, have begun to incorporate computer-aided engineering (CAE) programs into the existing design and analysis process, including 2D and 3D solid modeling (CAD). This method has many benefits, including easier and more exhaustive visualization of products, the ability to create virtual assemblies of parts, and the ease of use in designing, mating interfaces, and tolerances. Other CAE programs commonly used by mechanical engineers include product lifecycle management (PLM) tools and analysis tools used to perform complex simulations. These tools include FEA, CFD, and CAM. Using CAE programs, a mechanical design team can quickly and cheaply iterate the design process and develop a product that better meets cost, performance, and other constraints. If you do not know the meaning of iteration, repetition, redoing the thing and refining it in stages. No physical prototype need to be created until the design nears completion, allowing hundreds of thousands of designs to be evaluated instead of a relative few. In addition, CAE analysis programs can model complicated physical phenomena which cannot be solved by hand, such as viscoelasticity, complex contact between mating parts, and non-Newtonian flows. As mechanical engineering begins to merge with other disciplines, as seen in mechatronics, multi-disciplinary design optimization, called as MDO, is being used with other CAE programs to automate and improve the iterative design process. MDO tools wrap around existing CAE process, allowing product evaluation to continue even after the analysis goes home for the day. They also utilize sophisticated optimization algorithms to more intelligently explore possible designs, often finding better innovative solutions to difficult multidisciplinary design problems. Micron scale mechanical product components such as springs, gears, fluidic, and heat transfer devices are fabricated from a variety of substrate materials such as silicons, glass, and polymers like SUA. Examples of microelectromechanical systems, shortly MEMS components, are the accelerometers that are used in as car airbag sensors, modern cell phones, gyroscopes for precise positioning, and microfluidic devices used in biomedical applications. Friction stir welding, a new type of welding, was discovered in 1991 by the Welding Institute (TWI). The innovative steady-state non-fusion welding technique joins materials previously unweldable, including several aluminum alloys. It plays an important role in the future construction of airplanes, potentially replacing rivets. Rivets can fail. Just think of an airplane failing in midair. Current uses of this technology to date include welding the seams of the aluminum main space shuttle external tank, Orion crew vehicle, Boeing Delta II and Delta IV expendable launch vehicles on the SpaceX Falcon 1 rocket, armor plating for amphibious assault ships, and welding the wings and fuselage panels of the new Eclipse 500 aircraft from Eclipse Aviation, among an interestingly growing pool of users. Composites or composite materials are a combination of materials which provide different physical characteristics than either material separately. Composite material research within mechanical engineering typically focuses on designing and subsequently finding applications for stronger or more rigid materials while attempting to reduce weight, susceptibility to corrosion, and other undesirable factors. Carbon fiber reinforced composites, for instance, have been used in such diverse applications as spacecraft and fishing rods. Mechatronics is a synergistic combination of mechanical engineering, electronic engineering, and software engineering. The discipline of mechanical engineering, mechatronics began as a way to combine mechanical principles with electrical engineering. Mechatronic concepts are used in the majority of electromechanical systems. Typical electromechanical sensors used in mechatronics are strain gauges, thermocouples, and pressure transducers. At the smaller scales, mechanical engineering becomes nanotechnology, one speculative goal of which is to create a molecular assembler to build molecules and materials via mechanosynthesis. For now, the goal remains within exploratory engineering. Areas of current mechanical engineering research in nanotechnology include nanofilters, nanofilms, and nanostructures, among others. FEA is a computational tool used to estimate stress, strain, and deflection of solid bodies. It uses a mesh setup with user-defined sizes to measure physical quantities at a node. The more nodes there are, the higher the precision. This field is not new, as the basis of FER finite element method (FEM) dates back to 1941. But the evolution of computers has made FEA FEM a viable option for analysis and structural problems. Many commercial codes such as Nastron, ANSYS, and Abacus Q, are widely used in industry for research and the design of components. Some 3D modeling and CAD software packages have added FEA modules. In the recent times, cloud simulation platforms like SimScale are becoming more common. Other techniques such as finite difference method (FDM) and finite volume method (FVM) are employed to solve problems relating heat and mass transfer, fluid flows, fluid surface interaction, etc. Biomechanics is the application of mechanical principles to biological systems such as humans, animals, plants, organs, and cells. Biomechanics also aids in creating prosthetic limbs and artificial organs for humans. Biomechanics is closely related to engineering because it often uses traditional engineering, traditional engineering sciences to analyze biological systems. Some simple applications of Newtonian mechanics and material sciences can supply correct approximations to the mechanics of many biological systems. In the past decade, reverse engineering of materials found in nature, such as bone matter, has gained funding in academia. The structure of bone matter is optimized for its purpose of bearing a large amount of compressive stress per unit weight. The goal is to replace crude steel with the engineering aspects of crude steel with biomaterial for structural design. Over the past decade, the FEM has also entered the biomedical sector, highlighting further engineering aspects of biomechanics. FEM has since then established itself as an alternative to in vivo surgical assessment and gained the wide acceptance of academia. The main advantage of computational biomechanics lies in its ability to determine the endo-anatomical response of an anatomy without being subject to ethical restrictions. This has led FEM to the point of becoming ubiquitous in several fields of biomechanics, while several projects have been adapted to open source philosophy. Example, BioSpine. Computational fluid dynamics. There are so many short forms. Just to get used to the terminology first. The branch of fluid mechanics that uses numerical methods and algorithms to solve and analyze problems that involve fluid flows. Computers are used to perform the calculations required to simulate the interaction of liquids and gases with surfaces defined by boundary conditions. With high-speed supercomputers, better solutions can be achieved. Ongoing research yields software that improves the accuracy and speed of complex simulation scenarios such as turbulent flows. Initial validation of such software is performed using a wind tunnel and the final validation coming in full-scale testing. Example, flight test. Acoustical engineering is one of the many other sub-disciplines. We call it as sound engineering, of mechanical engineering and its application of acoustics. Acoustical engineering is a study of sound and vibration. These engineers work effectively to reduce noise pollution in mechanical devices and in buildings by soundproofing or removing sources of unwanted noise. The study of acoustics can range from designing a more efficient hearing aid, microphone, headphone, or recording studio to enhancing the sound quality of an orchestra hall. Acoustical engineering also deals with the vibration of different mechanical systems. Other applications are in manufacturing engineering, heat power engines, refrigeration and air conditioning, automobile engineering, design of products and equipment, and aeronautical engineering. The applications are numerous since mechanical engineering is one of the core disciplines of engineering. Nowadays, applications are multidisciplinary. For example, automotives are purely mechanical in olden days, but now, besides mechanical, electrical, electronics, instrumentation, computer engineering are also used. Mechanical engineers are at the forefront of developing new technology for farming, transportation, environmental remediation, safety, food production, housing, security, water resources, healthcare, etc. Mechanical engineering is a forefront of developing the latest technology in the following areas of 3D printing, also called as additive manufacturing, interconnected machines, Internet of Things, IoT, Industry 4.0, which is called Industrial Internet, IoT, digital manufacturing. Industry 4.0 is also called as the fourth industrial revolution or industrial IoT. Digital manufacturing, biomedical engineering, green manufacturing, nanotechnology, alternative energy, solar energy and other renewable energies, mechatronics, robotics, smart materials, composites, automation and intelligent systems, CAD, CAM, sustainability, agricultural technology, equipment used in agriculture, energy solutions, textile industry, self-driving cars, autonomous cars, and new automated transport solutions, manufacturing optimization, rapid tooling, project management, laser cooling, cryogenics, 4D printing technology, nano electrical, electromechanical systems, digital twins, hyperloop technology, computational fluid dynamics, CFD, industrial Internet of Things, IIoT, beamed energy propulsion, autonomous vehicle, a scramjet, supersonic combustion ramjet, fuel efficient engine technologies, high speed machining, advances in gas turbine technology, stir friction welding, agile manufacturing, advances in heating, ventilation, and air conditioning, HVAC. In other words, sky is a limit for application of mechanical engineering. That is no limit, in other words. Simple. All organizations, whether it be manufacturing or service, need mechanical engineers, so there is no certain depth for mechanical engineering and other core disciplines of engineering, which is civil, electrical, and electronics. Of course, life is cyclic. Ups and downs are common in job market. If the person has a passion for the work they do, success. The success is certain. Apply your mind fully, be innovative, have determination and willpower. Nothing is impossible. Impossibility is an impossibility. Two negatives. That means everything is possible. Believe in yourselves, your capabilities, have self-respect and self-esteem. Never underestimate your capacity. Nobody is born a genius or a fool. It is all in the mind, and if you are determined, nothing can stop you ever. Debates, discussion on open-ended topics like this can go on forever. Anyhow, let me pull the plug here. We'll meet again real soon with another interesting topic. Some of the statements used expressed are solely mine based on limited knowledge gained over 6 decades of versatile experience. Always watch these videos with the closed captions, subtitles for absolute 100% comprehension as per my sincere recommendation zillion times so far. I know I rushed through to complete within 20 minutes. That's a norm that I have set myself to retain the viewer's attention. But of course, nowadays I don't, I'm not able to stick to that norm that I have set myself because I make honest attempts to cover the selected topic more elaborately, in depth, including all the fine aspects, referring a wide variety of sources, in particular Wikipedia quite extensively, besides articles and books published recently. Besides, of course, I sprinkle my own salt and pepper and season it with my personal experiences so far in my life and also intuition. Stay at home as much as possible to maintain social distancing attributed to the pandemic novel COVID-19 and prolong your lifespan. Lead a healthy life. God alone can put a stop to natural and unnatural events, maybe bio war and cyber war events like pandemics, which may lead to apocalypse, that is the end of the world. an extinction of all sentient species on Earth for no fault of theirs. All of you can let me know your comments, irrespective of the nature of the comment. Okay, I'd like to hear from you so that I can refine my presentations in future. Rest in peace and harmony.